All right, so today we're going to talk about fossil fuels. Okay. What are the fossil fuels? Coal, oil, and natural gas. Okay. So we'll talk about how they form and the uses and how much longer will they last. Okay. Of course, for your generation's sake, we hope that we leave all of it in the ground. Okay. We don't. So, for instance, if the world uses coal at the current rate, there's still 1,200 years worth of coal, 1,000 years worth of coal. Of course, we don't want to use it all. Okay. All right. So we'll talk about that. So here's a rock that has this is shale oil. It has a lot of oil in it, and look at this. You can burn this rock. Well, you're burning the oil is what you're doing. So here's a rock that has plenty of oil in it. We'll talk about all these things. I'll let you guys read all that, but okay. So here's the deal. Fossil fuels, coal, oil, and natural gas are made from living matters. It's dead living matter. They're made over millions of years, and they were made close to 100 to 200 million years ago. Okay, so it's not like there's a drive-through where you can say, "Hey, make me a coal while I wait." Okay, it takes millions of years to make fossil fuels. They were made hundreds of millions of years ago. And the shame of it is we are using it all up within a matter of 50 to 100 years. In the blink of an eye. So what we are doing is we are releasing all this carbon that was trapped millions and millions of years ago into the atmosphere in a blink of an eye. You guys understand that?
Yeah. So what you said, please?
Okay, just one second.
So in the 1800s, when they were getting energy out of the ether, why did that change?
Energy out of ether?
Yeah, I mean, I'll talk to you one day after class.
Okay. Well, before oil was discovered, we used to use whale blubber to light lamps and stuff like that. And, so in that sense, oil is good. Now we stopped killing whales. But, all right. So they originate from organic, so living matter, okay, that has been subject to high temperatures and pressures. Yeah. So essentially, let me start off by showing you a diagram. Okay. So we'll first talk about how oil and gas are formed. Okay. And I'm going to go all over, but you guys can. Okay. The formation of oil begins in warm, shallow oceans. Okay. So oil is made in warm, shallow oceans. Okay. So here's the deal. Okay. So oil and gas are made out of small living things in the ocean. Plankton can be about from a millimeter to a centimeter size. So small living things like this. There are animals and plants, both animals and plants. The plankton. What is the difference between animals and plants? In this context, plants can harness sunlight and make food. Okay, photosynthesis. Okay, so these matter when they die, they fall to the floor. Okay, now if there is oxygen in the environment, bacteria can decompose them, and that gets recycled. Okay, so if you want to make oil and gas out of this, you gotta make sure that it doesn't decompose. Okay. And what is the way to not to prevent it decomposing? Well, you have to be in all oxygen poor environment. But the best way to do is cover it with silt. Okay. How would you cover it with silt?
Ash.
If there was rivers flowing in, okay, you could cover it with silt. Okay. Anyway, so you gotta start with dead organic matter. You gotta make sure that it doesn't get recycled. Okay. 99% of all dead things get recycled. Okay. About 1% get trapped. Okay. So you cover it with silt. And now you gotta apply pressure and raise the temperature to make oil out of it.
So that would be where amoebas would be able to be?
Yeah, so bacteria and stuff like that can recycle it, okay? But you're trying to prevent that.
Right.
Okay. All right, now you gotta cover this up and apply pressure and heat to it to make oil.
Covered with what you said?
I'm sorry?
Covered with what?
Cover it, so let's say there's a river flowing in, sand and silt will cover it, mud will cover it. Okay? You guys understand? All right. All right, so we're going to cover this. We're going to cover this roughly about 2 kilometers. 2 kilometers is from here to Beach Street. A little less than that, 2 to 4 kilometers. Okay. And does that happen overnight? No. It happens over 1 million years or so. Okay. So it happens over a long period of time. All right, so there, 2 kilometers of silt is not falling from the rivers and stuff like that. There's plates moving. Do you guys know about the tectonic plates? Everybody know about tectonic plates? Okay. So in 1 million years, a plate will move from here to St. Augustine. Okay. And what are you trying to do? You're trying to cover this stuff under 2 kilometers from here to Beach Street. Okay. All right, anyway, so the details, somehow the stuff has to be buried. So here's small organic matter that died. You covered it with silt, you buried it, and you've applied pressure. So all this stuff overlying is applying pressure, okay? And so this is at 15 degrees Celsius. At about 80 degrees Celsius, this organic matter becomes something called kerogen. Okay, it's a waxy, solid black stuff. Okay, and now if you heat kerogen further, it can become oil. If you heat kerogen between 80 and 160 degrees, it becomes oil. And if you heat it above 160 degrees, it becomes natural gas. Okay, so there's how you made oil. Okay, how long was this? This was millions of years, a few million years. Okay, so you don't make oil overnight. Okay.
I'm sorry, what did you say it gets covered with? I heard you say mud the second time. Silt?
Silt. Yeah, you know, when a river is flowing in, it's bringing in sand and mud and clay and stuff like that. That's what you're covering it.
Okay.
Why do you need to cover it? I'm sorry?
Stop oxygen from getting to it.
I'm sorry?
Just stop oxygen.
That's right. Otherwise, it would get recycled. Okay. So about 1% of dead matter gets in the rocks. Okay. So that's the process of oil, manufacturing oil. Yeah. Now, of course, this oil has rocks, water and stuff like that. Oil is less dense and it would rise. Okay. So this is oil-rich rock, and that will be a reservoir. And if you have a rock on top of it which prevents oil from coming up, now you have an oil reservoir. Okay. So here's a porous rock. Porous rock meaning rock with holes and stuff like that. That has oil in it. See, water is at the bottom, oil at the top, and here's gas. And here's an impenetrable rock, preventing that oil from rising and the gas from escaping. Okay? And if this rock was in there, all that oil and gas escaped and you don't have access to it. And all you have to do is bore a hole through it and pump it up. Very easy.
So the porous rock preventing oil to,
No, the porous rock, this rock has oil in it.
okay,
This impermeable rock,
oh,
that is preventing the oil from rising. Okay. Okay, how much oil is there? At 0% annual growth. Okay, so this is oil resources in the world. We have roughly 100 years worth of oil. Okay. Hopefully, we won't use it all up. Okay. Natural gas, 100 years worth of natural gas. Okay. And coal, at 0% annual growth, we have 1,000 years worth of coal left. Okay. We haven't talked about how to make coal, but we'll talk about that. So, you guys all know how to make oil and gas now. Okay? So, oil, yep.
The porous rock, is that created from the rising oil?
No. That, remember the silt and all that?
Yeah.
Oil was, yeah, that rock is porous. Okay, let's make coal now. Yep. All right, so you gotta start in swampy forests. Okay. You got trees, so to make coal, you're starting with trees. A tree dies, it falls into the swamp, and then you got to apply pressure and heat. How do you apply pressure and heat? You cover it with silt, and then you got to bury it underground. Okay. So over time, and again, you have time on your side. How much time do you have on your side? As long as you want. Okay. So you bury the stuff. Yep. Go ahead.
So the coal mines, like, you know, in the 1900s, 1800s, things like that,
Mm-hmm.
when they went into the mountains, they were actually, the mountains maybe were decomposed trees,
I'm sorry.
right? They were going into caves
Mm-hmm.
for the coal.
Right. Mm-hmm.
And I'm just saying in my mind, then maybe some of the caves were old trees.
Well, if it was a coal seam, okay, so let me show you a coal seam. Here's a coal seam. So here's land. Here's an impenetrable rock. Here's a oil deposit, natural gas deposit. Here's a gas-rich shale. This is okay. Here's a coal bed. Okay, so that is dead trees. Okay. And you have to get to that. So if this is close enough to the ground, you just dig up the soil and get to it. Okay, which is what done here. Okay, so if that seam was close enough, but if it's not close enough, you just dig a tunnel and get to it. Okay. This seam can be as wide as this building. And so I don't know, maybe as wide as this building and let's say a kilometer long from here to Krispy Kreme donuts. Yep. And just dig up the coal. Easy. Okay. All right, so let's make coal. Okay, so you start off with dead trees, cover it with silt, easy to do in swampy areas, bury it, okay? And then that's how you apply pressure, okay? And the longer you apply pressure, the more carbon content becomes in the coal, the more energy there is, okay? So this is still a mixture of coal, organic matter and silt, and this is a poor quality coal, and the greater pressure and heat you apply, the better the quality of coal. This is the best quality of coal, okay? This has 90% carbon and about 10% moisture. So this is the best quality coal. This is the most energy content per pound. This is what we use in the US mostly to produce electricity because this is what we have. Okay? Yep.
What exactly are
I'm sorry?
What are you burying with the dead?
Okay, so this tree was growing, these trees were growing in swamp. You cover it with silt, sand. You're always burying it with sand, silt.
Like, how are you burying the tree? Like, just,
Oh, the tree is growing in a swamp, it dies, it falls into the swamp.
oh, okay, so the whole tree,
Yeah, the whole tree.
okay.
Yep,
So coal mines used to be swamp area?
that's right. So how did they get to wherever they get? How did they get in the Appalachian Mountains?
Right.
Plate shifting.
Huh?
Plate shifting.
Plate shifting, that's what we do. So we forget that we have millions of years, and in a million years, how far will this plate go?
Up to St. Augustine?
Up to St. Augustine. There you go. Where was the oil and gas made? Under the oceans. How did it end up in Saudi Arabia? Plate tectonics. All right. All right. So we know the process of making oil and coal now. Okay. All right. Now we'll get to the boring details. All right. Any questions? We have to
I
go.
have a question.
All
How,
right.
are tectonic plates, they're like underneath the ground, so that's, they move, I was confused on that.
All right. Let's talk about that. All right. How big is the Earth? What is the radius of the Earth? 4,000 miles. Okay. And so let's say this is about 40 miles. I'm giving you rough numbers. That's about 1%. Okay. So think of a watermelon, and we are talking about the skin. Okay. So this, and right below that is rock that has melted. Okay. So it's plastic. This is called the asthenosphere. Okay. So what does okay, what happened was somebody took a hammer to the crust and broke it up into plates. Okay. Now, heat rising up. So think of wood pieces floating on honey. And heat rising up gets these plates moving. Okay. So these are 40 miles thick, and let me show you. So there are the plates. Okay, so you see that? And this plate is moving that way, that plate is moving this way. There is the mid-Atlantic ridge, and so hot magma is oozing out of there and creating new plates. Okay, all these plates are moving. They're moving about 2 inches a year, the same rate at which your fingernails grow. Okay, but given time, they'll move from here to St. Augustine in a million years. Okay, so they're constantly moving. So new plate is being created here. Okay, from these plates moving away. Well, so is the surface area of the Earth increasing? If new plate is being, so what's happening? Very good. So if you create an acre worth of new plate, you got to destroy an acre worth of plate somewhere else. Okay, and so if one plate is denser than another, it will subduct under the other plate and get destroyed. Okay. And if two plates are the same density, they'll bump into each other and make mountains. Okay. So here we go. So here's magma rising and creating new plates. Here's the subduction. This is what's happening in San Francisco, and any times. So this plate is, again, how thick is that plate? 40 miles, okay? And so when plates are sliding, well, they're constantly moving, but they can get stuck. And every time they slip, that's how earthquakes happen, okay?
So tsunami happened because it's
Okay, so a tsunami happened because this plate was going underneath there, and it's got stuck, and then when it slipped, an earthquake happened, and then that's under the ocean. Okay. All right, so to form colds, you need dead trees in a swampy area, cover it with silt, apply pressure, and warm it up, apply pressure and heat, and you'll get coal. Okay?
On the model with the coal and the oil together, is the oil generally below because it takes longer to make, or is it coal just like less dense and it's higher?
What do you mean?
Can you go to the model where it has the big old model, where it has the coal straight and also the oil?
Oh.
Is the coal considered to be throughout the model, or is the coal generally higher up in the
Oh, no, this is just a drawing.
model? Okay.
I mean, in one picture, they wanted to draw everything.
Okay.
Yeah. It could happen like that in reality too, but that's just a drawing.
That could be at any depth?
Yeah.
Okay.
Well, generally, all of this is within 5 kilometers, meaning from the beach to here. All right, so now I'm going to just point out the stuff that, I was reviewing this stuff earlier, and I'll point out the stuff I remember. But I trust you guys are going to read every bit of it, right? Yeah. All right. So the formation of oil takes a long time. 70% of the oil deposits was made 250 million years ago. 20% during the time of the dinosaurs. Okay? And only about 10% is about 500 million years old. Okay? But it's all very old. Oil began in the shallow oceans. Okay? Oil is made out of plankton. Plankton is small living things. Zooplankton is animals, and phytoplankton are plants, but about roughly this size. Okay? You'll see in detail. Okay, hold your cup up. Okay, so to make about that much oil, you need 20 tons of plankton, dead plankton, from here to the wall, about this high. Okay? And then I need a coffee from Wow. I'll just burn up oil. Okay, so the dead organic matter on the ocean floor mixes with organic material that enters the oceans by rivers. Okay, so what are you trying to do? This matter dies before it decays and gets recycled. You have to cover it with silt. Okay? And then apply pressure and heat. And how do you apply pressure? You got to get it deeper and deeper. Okay? So sink to the bottom of the ancient oceans. Okay. With the that enters the, okay. I don't want to read all of this. Okay. Dead plankton as well as algae and bacteria sink to the bottom of the ancient ocean and mix with inorganic clay-like material that enter the ocean from streams and rivers. Okay, so this creates an organic rich mud. This mud can only form in still water environments. Okay, it gives you all the details. Okay, so the mud cannot be exposed to too much oxygen, or else the organic matter in the mud would be decomposed by bacteria. Okay, so you got to make sure that it doesn't decompose. Then you have to bury it to 2 to 4 kilometers. Okay, 2 to 4 kilometers is, let's say, like I said, from here to Beach Street. Okay, between Nova and Beach Street. The increasing in pressure and temperature of the shale transforms it into a waxy material known as kerogen. So that dead matter, you apply pressure by burying pressure, and the deeper you go, the temperature increases. That dead matter gets transformed into this material, black material called kerogen. And if you heat the kerogen, you can either get oil or natural gas. Okay. Shale that contains this material is known as oil shale. If the temperature of the kerogen are greater than 90 degrees Celsius but below 160 Celsius, so between these two temperatures you produce oil, and that's called the oil window. Okay.
Stevie, what does, the Kara part mean? Like,
It's
where does Kara come from? Do you know that? Like, etymology of it?
Carol.
K-E-R-O. You know?
You have a smart assistant at your fingertips,
No, I
Mr.
don't.
Google.
I thought you might know that.
I'm not smart.
Well, Google changes things though, you know what I mean? Like,
What?
it's not always accurate anymore, so you
Um.
have to ask the people that have read the books first before they change.
All right, so at higher temperatures, you make natural gas. Yeah. Okay, rock bodies that contain significant amount of oil are known as reservoir rocks. Okay, so that's what you're looking for when you're exploring for oil. Yeah. For the oil to remain trapped, there must be a thick, impermeable layer of rock to seal the reservoir. Yeah. Geological changes in Earth's crust can bring these deposits closer to the surface or move them around the world and stuff like that. Okay. So, but you're forming the oil and gas in oceans. Okay, so here's the process again. Okay. We went through that. And this is the plankton from which you're making oil and gas. Okay. Again, living things about that big. Okay. Coal is formed with dead plant matter submerged in swamp environments. Coal is formed when dead plant matter submerged in swamp environments is covered by layers of dirt and rock. It is then subjected to heat and pressure over hundreds of millions of years. Again, how do you apply pressure and heat? Just keep burying it. Okay. How deep do you have to bury? Roughly 1 kilometer, 2 kilometers, stuff like that. Okay. Coal is categorized into 4 main types, okay, in order of increasing carbon and energy content. The more carbon there is, the more energy there is. Energy per pound, okay, and we'll come to that in a second. So you saw that. Anthracite has the most energy. This is 90% carbon, okay. So now here is the problem. All types of coal contain sulfur. Okay. When you burn coal, the sulfur gets converted to sulfur dioxide, which leads to acid rain. Okay. So since that's one of the problems. Well, the main problem is carbon dioxide, but acid rain is also a problem. Okay. High sulfur deposits come from brackish swamps or marine influence environment. Low sulfur coal deposits develop in freshwater environments. Okay. So if the trees died in brackish water, you end up with high sulfur coal. Yeah. And I believe the Appalachian Mountain coal is high sulfur coal. There's coal mines in West Virginia as well, and anyway, so. There's low sulfur coal in the Rockies, but do you want to dig up coal in the Rockies? No. Yep. all this coal comes from mines which are either underground or above ground. So you saw, depending on where that coal seam lies, if it's close to the surface, you just move away the dirt and just dig it up. Okay. All right. Underground mining remains one of the United States' most hazardous occupations, killing dozens of miners every year. Okay. So if you have a mine underground, they just go through the mine, and the pillars holding them up are coal pillars. And then, since we're greedy, as you're backing out to get the last bits of coal, you pull those pillars out as you're backing out. And the tunnel could collapse. All right. So, remember you took plankton, those tiny organic matter, and covered it with silt, applied heat and pressure, and that became kerogen. Okay? So kerogen is sort of a store for carbon. Okay? It's ancient dead matter. Okay. Organisms are dying all the time on the surface of the planet. When organisms die, they decay, and almost all parts are recycled and reused quickly by the biosphere. Okay. About 1% of the dying biomass sediments. What does that mean? It dies and it gets covered by silt and dirt, and it's not recycled. Okay, that is, it gets included in the forming rocks or mineral layers of sediment origin. All sedimentary rocks, okay, so what are sedimentary rocks? Okay, the silt that gets to the bottom of the ocean, that gets pressed, that's sedimentary rocks. Okay, so rocks made out of sediments. Okay. Becomes trapped, so therefore including a fraction of organic matter that becomes trapped in the forming process, creating organic shale. So this rock has organic matter. And if there is a lot of organic matter, you saw that you could burn it. Okay, you saw that picture. Okay, so that would be oil shale. If this shale is buried between 2 and 4 kilometers, its temperature increases. This increasing pressure and temperature of the shale transforms that organic material into kerogen. Okay? So you take dead matter, press on it, and it'll become kerogen. You keep heating the kerogen, it becomes oil and gas. Okay. If the kerogen is continuously heated, it leads to slow release of fossil fuels such as oil and natural gas. Okay. And also graphite. Graphite, somebody hold up your pencil. Your pencil lead is graphite. Okay. So you can make, so that's dead organic matter. Okay, that graphite. All right, how much kerogen is there? Okay, there's 10 to the power of 16 tons of carbon in kerogen in the earth. Okay, all right, what does that mean? It's the most important abundant source of organic compounds on earth, exceeding the total organic content of living matter by a factor of 10,000. Okay, if you take all the living things on earth today, the carbon content of all the living things on earth today, 10,000 times that is what's in the kerogen in the planet today. Okay. Upon heating, kerogen converts it's in part to liquid and gaseous hydrocarbons. Okay, so if this was the amount of kerogen, okay, so 10 to the power of 16 tons. 1 ton is about this much water. This much water is 1 ton. 1 ton is the weight of a small car. Okay. So 10 to the power of 16 is 10,000 trillion tons. Yeah. Out of that much is coal. That much will be coal. Okay, and that's natural gas and shale oil and so on. Okay. All right. So now before, let's say you were living, I don't know when coal was discovered, but let's say you were living in the 1500s, 1700s, what would you do? You'd cut up a tree, use wood for fuel. Okay? And then you replant trees, and that's a carbon net zero strategy, carbon neutral strategy. For every piece of wood you use, if you plant a tree, okay, the carbon dioxide levels wouldn't go up in the atmosphere. So if we go back to that, that would be a good strategy. Well, why did we switch from that? Okay, so so this is the amount of megajoules per kg. What is a kg? That much water is a kg. A kg is 2.2 pounds. Okay. So the energy content of wood is that much. Look at coal. It has 3 times the energy per pound. Okay. So the higher the energy content, that's what you're looking for in an energy fuel source. Okay. Oil has 33% more energy than coal, and it's easier to transport. You can pump oil from Alaska to Florida in pipelines. Okay. To transport coals, you would have to put it in trucks and stuff like that, and that costs more. Okay. So what are we looking for in an energy source, in a fuel source? We're looking for the highest energy density and the cheapest and the easiest to use. That's what we're looking for. Okay. All right. So we use fossil fuels because they have high energy densities. See, these fossil fuels have much higher density than wood, 3 to 5 times that of wood, and they are inexpensive. You just pump up oil. You just have to find it and stick a pump up there, and you pump it up. Okay. Or dig it up. And if you get lucky, the coal might be just under the surface, so you just dig it up. Buy a couple of earth movers, and you have, you have a source of income and become billionaires. Yep. Okay. However, there are long-term consequences. Wood can be carbon neutral if one replants trees. Okay. Unlike wood, fossil fuel use releases carbon dioxide into the atmosphere that was trapped millions of years ago. Yeah. And carbon dioxide, of course, causes global warming. So, a little history of oil. Oil was formed 250 million years ago, like we said, roughly. The efficiency rate of making oil from carbon from plankton is about 10,000 to 1. So what this number is saying is you take 10,000 pounds of plankton and you make 1 pound of oil. Okay, like I said, 20 tons to a liter. Okay. So again, from here to the wall, you take that much dead plankton and you get a liter of oil. What's that? That's right. That's right. I can't emphasize this enough. Here's a product that took millions of years to make. It was made 250 million years ago. And what are we doing? In 50 years, we're burning it all up. Yep. So oil was first discovered in the mid 1800s. Okay. So here, this shows you the oil deposits around the world. Okay. Saudi Arabia has a lot. Venezuela has a lot. And Canada has tar sand and all that kind of stuff, and we'll talk about that. Okay. So in the world today, we produce 30 billion barrels of oil every year. 30 billion barrels. In the US, we produce about 3 billion barrels, about 10%. Okay. 30% of the world's energy comes from oil. Okay. Okay. Now, here's something called the Hubert model. What the Hubert model says is any resource, oil, coal, or natural gas, when you first discover, you're trying to figure out a way to how to efficiently harness the source, and then you're looking for various deposits and stuff like that. So the use of this source increases, and then it'll peak once you've found all the sources and stuff like that. And then you deplete the sources. Okay, so you'll run out of. So, for instance, oil. So this is Hubert model for oil use worldwide. So we are roughly near the peak. That's what we believe. Okay, and so now we'll start using up oil, and then it'll all get over. Okay, so in 100 years, all the oil will be gone. Okay, by 2100, all the oil will be gone. That's what the model says. Okay, so the U.S. produces 3 million barrels of oil per day, per year. Okay, so that's the 10% of oil production. Saudi Arabia produces 4 billion barrels per year. Okay, now here's the deal. In the U.S., there are 600,000 oil wells. Okay, that much oil is produced from 600,000 wells. In Saudi Arabia, more oil is produced by only 1,000 wells. Okay, there the oil is very easily accessible and the tank is bigger. Okay, in the U.S., hold your cup up. That's how much oil is being pumped per minute from an oil well. Okay, we have depleted the oil. In Saudi Arabia, this much oil is being pumped every minute. That's a gusher. Yep.
You said the world does 30 billion barrels. What was the US?
3 billion, 10%. Here's the number. Yeah. All right, when you pump up oil, of course, you can't just put it in your car. It's got a mixture of all kinds of stuff, 500,000 different compounds. Okay. Now the thing is the following. So here are these compounds. What is this? This is methane, 1 carbon, 4 hydrogen. This is ethane, 2 carbons, and so on. These are called alkanes. They're just chains of hydrocarbons. Okay, and the heavier the hydrocarbon, the higher the boiling temperature. Okay, it makes sense. Heavier the molecule, harder it is to vaporize it. Okay, so when you pump up crude oil, it's got all kinds of hydrocarbons, and the heavier ones are harder to boil. Okay, and so when you pump up crude oil, that's what you want to do is you want to separate it into its components. Okay, and so you take crude oil and send it through a furnace, heat it to about 400 degrees Celsius, okay, and then pass it through a fractioning column. In this fractioning column, the different temperatures are maintained at different regions, at different heights. So here's a picture of a fractioning column. So here's a picture of a fractioning column. This is in an oil refinery. Okay. All right, what are you trying to do? You're trying to separate the components. So here's crude oil. All right, so you're maintaining this at 350 degrees Celsius. Okay, so anything that is still liquid below 350 degrees Celsius, that'll fall here, and you can pump it out. Okay, so this is 350 degrees Celsius. Okay, so stuff which remains liquid below 350 degrees Celsius is liquid, and you pump it out here, and that's asphalt. Fuel oil, its boiling point is around 350 degrees Celsius. So at 400 degrees Celsius, it's become vapors. But when it comes here, it becomes liquid, and it comes out of here. And you can use that in ships. Yep. Stuff that vaporizes about 350 degrees Celsius rises up. It rises up here. And then, so lubricating oil, this is a liquid. So at 350 degrees, this is vapor, but at 300 degrees Celsius, lubricating oil is liquid and it comes up. Okay. So that's how you separate different compounds. Okay. And if it's coming out at a higher level, that means it's a smaller molecule. Okay. And it's got a lower boiling point. So this is gasoline, petrol that comes out at 70 degrees Celsius, and what's finally left is natural gas or refinery gas, okay, which is essentially natural gas, okay, and you can use that to barbecue. Okay. So what you have is, this is how crude oil is refined. Okay. So out of a barrel, 42 gallons per barrel of crude oil make about 19 gallons of gasoline. Okay. And then it tells you 4 gallons of jet fuel. Jet fuel is kerosene. Okay. And so on. And that's what Elon Musk also uses for his rockets. And so on. All right. So this is the refining process. So crude oil is refined into useful products such as gasoline, diesel fuel, asphalt, fuel oils, heating oil, and petroleum and stuff like that. In general, heavier hydrocarbons, heavier the hydrocarbon, higher its boiling point. Okay, and they can be separated by allowing the vapors to travel up a fractioning column. This thing is called a fractioning column. Okay, with progressively lower temperatures. So this shows you, okay, all the various products and their boiling temperature range and so on. Alkanes are hydrocarbons. Okay, so again, you can, here's how a chain looks like. So, and you can extend this chain to as long as you want. So plastics are like that, okay, and so on.
You said
One,
heavier
two,
the
three,
hy-
four.
sorry.
I'm sorry, go ahead.
You said heavier the hydrocarbon, heavier the what?
Higher the boiling point. I mean, lower, yeah. Mhm. Heavier the molecule, harder it is to vaporize it. Okay. Okay, so this is a 4-carbon atom, and okay. So octane, your octane rating on your gasoline is this molecule. It has 8 carbons. Okay. And so octane rating is related to how much octane you have. Okay. So you saw that oil deposits are trapped under impermeable rock, and there'll be an impermeable rock at the base, and then the porous rock has the deposit. Now here's an oil deposit, and of course you want to get the oil out, right? So here's something that most people don't know. How much oil do you think we can get out? I'm sorry?
80% of that, 'cause
I'm sorry?
looks like, from the model, at least looks like only 50% of it or so, is the size you're not gonna be able to pump out.
50% was the right guess, except that the reasoning was so.
Unless you pump stuff in to pump the oil out.
So okay, so we'll talk about this. His guess was right. Only about 50% of the oil can be extracted, and so let's see how to do that. Okay, so oil and gas are usually trapped within porous rock that act as reservoirs. The reservoir has a cap of impenetrable rock. Okay. When a well is first drilled, initially the underground pressure forces oil up and gas up. So you don't have to do much, but about this way, without doing anything, you can extract about 10%. Okay. And then you have to start pumping and so on. Additional recovery is achieved by injecting water into the reservoirs to provide increased pressure. So you pump water in, force the oil out of the rocks, and then pump the, okay? Then by doing this, you can extract up to a third of the oil. With secondary recovery, less than a third of the oil is in the reservoir is taken out. Okay, so now you extracted a third of, so if there were 1,000 gallons, you've extracted 300 gallons. You don't want to leave money on the table, do you? All right. Tertiary methods include injecting steam. Why would you inject steam?
The heat and the moisture would help separate it.
The heat would make the oil less viscous, okay, and then make it flow easier out of the rocks. Okay. Heating the oil makes it less viscous, allowing it to flow more easily out of the rock. Some polymers are used to force the oil out of the reservoir rocks. You're using chemicals. And what is the concern with that? Then you're potentially polluting groundwater and stuff like that. If that chemical gets into your groundwater. Even with all the enhanced techniques, over 50% of the oil is still unextractable. Yeah? Maybe a blessing in disguise.
Yeah, because the earth needs it.
The earth doesn't need it. We don't need it above ground. Okay. Cracking. So when you get all this oil up, which has heavy components and stuff like that, what you can do is if you have a large hydrocarbon molecule and it's not useful to you, you can just break it up. Okay? You can break this up into, I'm just making stuff up, but you know, but we've been doing this all semester, so why would we stop now? All right, so we broke that molecule into by adding hydrogen. Okay, this is a process called cracking. And why would you do this? This is not as useful, this is more useful. Okay? Yeah, so you can make a bigger molecule into gasoline, diesel, or whatever. Okay? So, and that's the process of cracking. To optimize the use of our petroleum resources, it's necessary to convert some of the less needed refinery products to more needed forms. In most cases, this involves breaking down heavy hydrocarbons to make lighter hydrocarbons. Okay? Involves heating to a high temperature. Okay. Gasoline typically contains about 500 different hydrocarbons that have between 5 and 12 carbon atoms per molecule. The average density is about 720 kg per meter cube. A substantial fraction of these hydrocarbon components of the gasoline have the molecular mass similar to that of octane. Again, that's by the octane rate. Yep.
This is off topic, but
Mhm.
I have to leave in a couple minutes for a meeting. Can I take the quiz after my meeting?
See, I knew you were leaving, and so I didn't make the quiz today.
Oh, okay.
Are you on a team? Are you on a team? Are you an athlete?
No,
Oh, good.
no.
All right. Natural gas. So, natural gas is 85% methane and 15% ethane, I guess C2H6. So natural gas generally is found along with oil, or it can be found on its own too. Okay. Okay. So the formation of you remember kerogen. If you heat kerogen above 160 degrees Celsius, you get natural gas. Between 90 and 160 degrees Celsius is oil. Okay. Yep.
What was the 15%
Ethane.
again?
Okay. Here.
I think.
Mhm. So I will open the test later.
Oh,
Yeah.
so there is a quiz.
No, there's no quiz. I mean,
Oh, you didn't say it.
yeah,
Yeah, I'll
yeah.
do it.
Okay.
Thank you.
Yep, no worries. Okay, so this is the world's natural gas deposit. Russia has the greatest natural gas deposit. Okay, and so on.
So you said 90% what?
85%. 85%.
No, you said if it is 90%, what you mentioned, anyway,
That was coal.
okay.
Yeah, 90% carbon in coal. That's the best coal.
Okay.
That's anthracite. We'll come to that in a second. Okay. I'll show you a table. So Russia is the most natural gas. And again, we are burning, when you burn methane, you're combining with oxygen. And again, this is the culprit. Okay. And this is what you're after. Okay. So you burn 1 kg of natural gas and you get 55 megajoules of heat, energy. Okay. Natural gas, of course, is gas. In its gaseous state, natural gas is transported easily over land through pipes. Okay. But what if you have to transport it across oceans? Then you have to liquefy natural gas, and that's an expensive process. And this has to be transported at minus 165 degrees Celsius. Okay. So this is liquid natural gas, and that's expensive too. So sometimes they just burn it away because it's too expensive to transport. Fracking. So here's rock containing natural gas.
There's a lot of controversy on that.
Oh, yeah.
You don't hear about it a lot, you know what I mean, like 15, 20 years ago.
Right. Yep. All right. So here's the problem. So let's say this is a rock, and here are air pockets which contain gas. How do you get to that? I'm sorry? If you crack the rock, all that gas would come out. And that's what fracking is about. Okay? So fracking is often used to enhance natural gas recovery. Water with chemicals added, for various reasons, is injected into the well under pressure to fracture the rock and allow gas to enter. So you fractured this rock, and then gas will enter through this thing. And you also put sand and stuff like that to keep fissures open. And then gas escapes and comes, and then you harness that, extract the gas. This technique is controversial because of potential contamination of water supply with fracking liquids or natural gas. Fracking we've been using it since the 1940s. Coal, the earliest plant growth on land occurred about 350 million years ago, and these early forests are the origin of the oldest coal deposits. So coal deposits can be about 300 million years old. Okay. Okay, so there are the 4 types of coal. Higher the carbon content, higher the energy content, megajoules per kg. Okay, so this is the worst type of coal. It has only 25% carbon. The best type of coal has 90% carbon, and you see the energy content is almost 2.5 times greater. Okay. there's something called coke that's used in the steel industry. Okay, so what is made by heating coal to about 1200 degrees Celsius in the absence of air. Volatile materials are driven off and essentially pure carbon is left behind. So what you want is pure carbon. And you just start with, let's say you start with anthracite. You just have to drive away the moisture and all the other content, volatile content. Okay. And you need this in the steel industry. So here's an open pit mine. The removal of topsoil and vegetation in strip mining without replacement leads to erosion. The exposed land is not capable of supporting vegetation and wildlife. Over half the U.S. oil comes from the Appalachian region. However, coal from the Midwest and West have low sulfur content. Why do you care about sulfur in coal? I'm sorry?
Acid rain.
Very good, my friend, you were awake. So here's where we use coal. 70% to produce electricity, 20% for coke, which is used in the steel industry. Okay. The world has about 1,200 years worth of coal. Okay, so we haven't hit the Hubert peak for coal yet. And the graph is very wide. Here's oil shale, just oil-rich rock, and so organic matter trapped in sedimentary rocks turns into oil over millions of years. Some deposits are so rich in oil that the rock can burn. Okay. Now, we have the largest deposits of oil shale. Okay. So what you could do is you just dig up this rock, crush it, pass steam through it, and extract the oil. Of course, it's environmentally very damaging. It's an expensive process. And are you going to dig up shale from national parks, which are beautiful places? Okay. So, in the U.S., most of the shale that is rich in oil is found in the Green Rivers area of the Rocky Mountains. Yeah. It's estimated that about 600 billion barrels are economically recoverable. 600 billion barrels, that is, you could run the world for 20 years, the entire world for 20 years. Okay. The shale is mined and crushed and heated to 300 to 400 degrees Celsius to release the oil. In rich deposits, more than 30 gallons of oil can be extracted from a ton of shale. Okay. Again, a ton of shale. A ton is roughly that much, half of that thing. And you can extract 30 gallons, or roughly that much. So here are the oil shale resources. Shale oil production releases significant pollution and greenhouse gases. In Estonia, 97% of the air pollution comes from the shale oil industry. In Estonia, all of the pollution is from the shale industry. Okay. Extra heavy oil, so here's a different form of oil. This is very viscous, it's very hard to extract, expensive to extract. Venezuela has most of the heavy oil. Okay. This is tar sands. Okay, sand mixed with the heavy oil, or tar sand contains a highly viscous asphalt-like oil called bitumen mixed with sand. Okay, so what do? You just dig up the sand, heat it. Okay, pressurized hot water can be injected into well, and to recover the oil, the sand is mined and mixed with hot water or steam to extract the oil. Okay. Yeah. and the largest source of tar sands is in Alberta, Canada. Of course, if the tar sand is underground, then pressurized hot water can be injected into a well, and after some time, the oil mixture is extracted.
So could that, I have a question, so with the fires that they're having right now, could it be because it's hitting certain spots where there's
Uh,
oil?
No, the fires are forest fires. Yeah, well, I don't know, yeah. No, I don't think the ground is on fire. So this is tar sand resources. Canada has the most. Okay. Again, lifetime of resources, we have a 7,500 years worth of oil, 700 years worth of natural gas, and 1,000 years worth of coal. All right. So your homework is to go home and make coal and oil today. And then I'll open up the exam.